the behaviors of waves. The first one is a very simple one, so therefore this one should not be an issue at all. All right. The first wave behavior is one that you guys have done your entire life. All right, and that is reflection. Now, I mean reflection in the literal sense, not in the philosophical sense of let me think back and see. Let me reflect on how my day was. That I don't care about. All right, that's not what we're talking about here. Okay, a reflection here is simply a bouncing off. Okay, so when a wave hits an object, it can bounce off that object. When it bounces off, it has a name. It's called reflection. Light waves can do it. When light waves do it, you even call what you see the word that we're talking about here. You'll say, I saw my reflection. Okay? What is that reflection though? When you say you see your reflection, what do you actually see? Yourself. Okay? You see yourself. Now, what we'll also notice though is this though. When you see yourself, so for example, that's why I have a picture there of a young lady looking in the mirror. Okay? When you see yourself in the mirror, the question now is this. Is it exactly correct?
Yes.
No.
No? Okay. What would be incorrect about it?
It's kind of a switch. It's
Kind of switched? What do you mean by that?
The size is pretty much like reflected. So
Hold on, you can't use the word reflected when we're trying to describe reflected again. You love doing that for some reason though.
It's hard to explain,
But you said the mirror, what you see in the mirror is incorrect. How is it incorrect?
Okay, so if you got like words in your shirt, if you look at it through the mirror, it's going to be backwards.
Good. Backwards. What you see is backwards. As a matter of fact, it's even got a name for it. It's called a mirror image. Okay? When you use the selfie camera, right? When you use the camera on the front side of the phone, right? You'll notice that when you take a picture, what you actually see ends up being flipped. Because again, what it is doing is it's taking an image, but again, because you're using the front-facing camera, it's got to flip the image to make it look like the other side. So usually what happens is, well, let's look at this image right here. Okay? I'm talking about this young lady right here. What arm is up toward her mouth?
Right.
Her right. But if you look in the mirror, it looks like it's which arm that's up toward her mouth? Left. That's actually called a mirror image. When they say mirror image, they mean it looks the same except that it's flipped. Okay, that's all a mirror image is. But that's what we're talking about in the case of reflection. Reflection simply is when a wave bounces off. Now, not all surfaces can reflect things, right? Usually, what are some things about a surface that would reflect? What are some kind of characteristics of a surface that would be good for reflecting?
Shiny.
Shiny, go ahead. What else?
Hey, the type of material is
Okay, what type of material? Like, give me an example of a material then.
metal.
Metal, okay. So what else do you notice about metal? Describe texture.
It's kind of
Smooth, all right? You know what I mean? Because it's got to be able to, for it to bounce off, it's got to have something that's easily to hit, and then it can just literally, again, bounce off, all right? So again, that's what we're dealing with here. The wave bounces off, okay? It doesn't pass through. If it passed through, it would be one of your vocabulary words. What does it mean when the light can pass through?
Transparent.
Transparent, okay? But a mirror is not going to be transparent because it can't be transparent if it's bouncing off because that's literally the opposite of transparent. Transparent means I can see through. Mirror is going to bounce off, so you cannot go through. You cannot see through. Okay? Are we good with that? Now, this diagram right here, we're gonna draw, but I'm gonna draw it in a different way. Okay? But we need to know this diagram right here because I need this is what we call the law of reflection. All right? And the law of reflection has to do with these two words right here that we want to make sure we understand: the angle of incidence and the angle of reflection. Okay? But I'm gonna draw that one a little bit easier. I'm gonna draw it in a way that's probably better for you to kind of see. So what I'm gonna do here is cover that up. And we're going to draw this same thing. All right, but we're going to draw the mirror. This time we're going to say, here's our mirror. Okay, in case you came. It's a mirror that's laying down flat. So we're looking at the side of the mirror. Like, the mirror's a piece of glass, right? All right, so we put the glass on the side, on the table, and we're looking at it on side view. Okay, so what happens here is this. Let's say over here we got the sun. Okay, the sun sends out light, correct? That's the wave. So what happens is when that light wave hits the mirror, okay, that has a name. Meaning the beam that hits the mirror has a name. That name is called the incident ray. Okay, that's called the incident ray. And then depending on the angle that it hits the mirror with, well, that will determine the angle that it bounces off the mirror with. Remember we talked about that third law of motion? The third law? Somebody impress me by saying they remember what the third law said. Nobody's going to impress me. Some of you could, you just don't like to talk. This is my first period. The deathly silent class.
Third law of thermodynamics.
Nope. Third law of motion. It's the one that you've known almost your entire life. For every action, there's an equal and opposite, right? Equal and opposite. So if the ray hits at this angle, then what the law of reflection says is it's going to have to bounce off at the same angle. Sorry. So the angle that it bounces off has a name. That's called the reflected ray. So you have the incident ray, that's when it strikes. Then you have the reflected ray, that's when it bounces off. Okay? Coburn, is that light in your face? If it's bothering you, you can move. Okay, just saying, but if it is, it'd be bothering me. I can't have it when something's just shining in my face like that. All right? Like every time the cop pulled me over. Gotta shine that flashlight in my mirror so it goes right in my eyes. All right? I mean, he does it every week. I don't understand why he has to do it. All right, so. All right, speaking of bright lights. All right, so here we go. Right here, we have an angle. And over here, we have an angle. Angle A, angle B. Okay? Angle A is called the incident angle, or the incidence, the angle of incidence. I'll just call it incident angle. B is called the reflected angle. But what the law of reflection says is it says the angle A equals the angle of B. Okay? That's what the law of reflection says, which kind of matches up with the third law of motion. For every action, there's an equal and opposite reaction. All right? But that's what I want to make sure. So, like, I doubt that, like, it'd be great if they asked you something in pertaining to just, like, looking into a mirror. What is that called? Reflection. But I have a feeling that when they ask you something about reflection, it's going to be pertaining to incident and reflection. So you need to make sure you remember the word incident, which is strikes the mirror. Reflected is bounces off, because that's what reflection actually is. But then those two angles created by those two rays, those are equal to each other. They're equal. And again, if you can't remember that, like if you remember the third law of motion, then you should remember this one automatically. But I can't guarantee all those things because I don't know what's in your head sometimes. All right? Anybody have any questions about the law of reflection? It's simple. Like, this isn't complicated stuff today. All right? But we just got to, sometimes we got to throw names at it. All right? Like, how many of you had biology already? I think I've asked this like 5 times already. Only 2 people in this room have had biology. 3. Okay. So you had biology, right? There was a section there where you're talking about behaviors. Okay? Well, I assume you learned something about behaviors. And most of the behaviors you were familiar with, you just didn't know the names for them. Okay, like for example, you heard of like a horse, right? You know how you train a horse sometimes to, horses sometimes get scared by sounds, and so you train it so that way when they hear the sound, they don't get scared anymore. Like you've been familiar with that kind of behavior most of the time. You understand it, but you probably never knew that behavior was called habituation. Right? Well, that's the same thing. Like you're going to understand most of these concepts, but you probably didn't know what the names of these concepts were in the reality. Okay, you understand the idea, you just don't know the name of the idea. All right, can I erase? Say no if I cannot. Hear no no's. All right. So that's reflection. By the way, you want to know why today can be confusing to you, which is why I say you need to really focus on the names. Because reflection, what's the other word over there in the box? Refraction and diffraction, right? So imagine, you say kind of quick, reflection, refraction, diffraction, right? They sound all the same. So they all had that same sound. So when you go, hold on, which one is the bend? And 2 of them deal with bending. So when you go, that bending, oh, that's the refraction one. Was it refraction or diffraction? I don't know, right? And as soon as you second guess yourself, I'm going to win. All right, because on my test, if you go, hold on, is that refraction? As soon as you do that, you got the question wrong. That's usually what happens. When you second guess, you get the question wrong. All right, are we ready? Let's go to the second one. The second one is the one that impacts your life. Well, let me rephrase that. Well, I would say the first one, before smartphones, reflection was the one that was the most important because y'all had to look into a mirror. But now with smartphones, you don't need a mirror. You just look into the camera that faces the front of the phone. And that's why y'all's generation is the most narcissistic and selfish generation. Want to know why? Because you think you're so important that people want to see 50 pictures of you a day. The selfie generation. Huh? They do? I'm pretty sure the world will not fall apart if you don't.
Mr. Science,
Yes, sir.
did you send Ashanti Jones to sign out?
She's not here today.
Oh, she's here. I guess I gotta find out where she's at. All right, thanks.
Uh-huh. Interesting. Got that on video too. All right. Refraction. Now remember, reflection was what? What was the key word in reflection?
And it bounce off.
Dude, ready? I don't write definitions like you do. I don't say reflection. That's when things reflect. Because then everybody's going to go, well, what's reflect mean? So what does reflect mean? Bounces off. That was the key word there in reflection. Bounce off, right? The key word here, better circle it for Donovan, all right, is bending. Okay? This is not going to bounce off. It's going to pass through. All right? So let me make sure we understand that. Mirrors, light doesn't pass through. Glass, light does pass through. But when it passes through, it bends. That bending is what we call refraction. Okay? So they're very similar. Both of them include light hitting glass. It's just what happens when they hit the glass. Some bounce off, reflection. Some pass through, but bend, refraction. Okay, that's what we just need to make sure we understand that right there. Now, the whole other area here is this. Well, why does it bend? And the reason why it bends is because the light is going to change its speed. Remember we said that the light had a speed, right? I think it was like 299 million or something like that, 748,000, right? That's J-Lo looked it up. Okay. Well, what happens is when that light wave hits that glass, when it hits that piece of glass, it slows down. Just like when you're driving and then suddenly you see a cop, you slow down. All right? When you're driving and suddenly there's an accident, you slow down. Okay? So there are things that get in the way that cause it to change its speed. Well, that change in speed causes it to bend. That bending is called refraction. Now, refraction is a very, 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 very important part of your life. Matter of fact, right now, you're able to write this off the screen. It's saving me from having to write all this on the board myself because there is a piece of glass right there that's projecting this onto the screen. All right, for example, if I take this piece of paper, I can project it onto this piece right here, right? But is that clear? No, that's because of the piece of glass. All right, it's bending it, right? So like this screen right here, it's out of focus. Jayla has the same problem. Zyquez has the same problem. Okay, that's why they need an extra set of lenses, which is the piece of glass that's bending the light, so that, because right now, if they take these glasses off, what they see looks like that. Because their eye, the back of the eye, has a thing called a retina. The retina is a movie screen, okay? It's where the picture gets displayed. But the problem is, their eye lens is not focusing right on here. It's like the piece of paper. It's blurry. That's what I'm looking for. It's blurry, so they need another lens to bend it even a little bit more, so that then when it shows up on their eyes now, they can see clearly. All right, so that's the same idea. Okay, so eyeglasses, contact lenses. Okay, lenses on that projector so that I could make it display on this board, and not have to, move that projector all the way to the back of the classroom. Matter of fact, I know Mrs. Brody. She has a projector that sits right on her counter. All right, hers sits right there. But she's also got this other lens that's attached to that so that it can sit right there and project to the board. All right, I don't get that lucky. So I got to do what I got to do. Like, I used to have these TVs work, right? But then one broke. And then when this one worked, they couldn't read anything. So I said, screw this. I'm getting my projector, put it in the middle. All right, and then now they ask me all the time, do the TVs work? I have no idea. Don't matter. I found my way. So the reason why, the way I gave you this example right here because of this. Like if you're running, all right, which, I've done that one time in my life. But if you're running, where do you run faster? If you're running on the sand at the beach or if you're running in the water? Well, where's easier to run? In the sand, right? So imagine you're running on the sand and then all of a sudden you run into the water. Your speed's going to slow down. Well, that same thing happens to light. When it hits a different medium, Eric, what is a medium again?
Material.
The material that the wave is passing through, right? When it goes to a different medium, it probably changes its speed. Okay? And that's how these things get created. So now just take a look at this. You don't need to write them down so much. But like right here, see how that image is now, we call it distorted. It's been altered. It's been changed, right? Well, that's because, again, you have water in the glass. You have a glass. So the light now, literally the first thing that happens is the light wave, it hits the glass. That changes the speed. Then it hits the water. That's a liquid. It changes the speed even more. And that's why you get that distorted image. Okay? Over here, what is this right here? Rainbows. You get rainbows because of refraction. Okay? That's how you get a rainbows, from refraction. All right? Right here, you ever have this moment? Oh, let me go ahead and erase that. Sorry. You ever have this moment where you're drinking? You know, I know you have a pencil here, but sometimes you had a straw in the glass, and then you look at it from the side, and then it kind of looks like it's been broken. Right? That's an optical illusion. Optical illusions are based on the physics of refraction. That's what it is. Okay? This one right here, you probably don't get, so I'll kind of demonstrate it right here. It's really, really simple. You can do, if you have a little kid, you'll see their head explode. All right?
Oh, this one, that little pen.
Yeah, you just take, you take this right here. You take a coin, right? There's a penny. Then you get a glass of water, and you set it on top. When you put it on top, and they're looking from the side, the penny disappears. Right? They kind of, I know I blocked your view, so, you know what I mean? But, the whole scenario here is this. I'll do it over here by George. So again, remember now, the key here is you got to look at the side. Because remember, it's an illusion, okay? The penny did not really disappear, all right? If it did, you wonder where it went. So, right here, you take it, you see the penny. When you put the glass on top of it, though, if you're looking from the side, the penny disappears. All right? So people go, holy crap, right? Well, that's kind of the whole thing. Because, again, the water in the glass bends the light. So it bends the light now so that it kind of it moves the image to the side, just like it moved that pencil to the side. It moved it so far that it's out of the field of view. All right? Now, if you look from the top, the penny's right where it is. But that's kind of what we're dealing with there. Another one right here. Like, here's one that most people don't actually realize. So here I have a glass of oil, right? I have a glass of oil. I got tongs around here somewhere. Of course, people in the video are going, what the heck is he doing right now? Oh, here we go. So I got a glass of oil, right? But what you probably, if you've been staring at the glass of oil, what you probably did not notice is this. That inside this glass of oil, I had another glass. Okay? You know what I mean? And the whole point is, because the oil and the glass have the same refraction rate, which means it bends it at about the same rate, you can put this thing and basically it's hidden. The only way you even know it's in there is if you can see that. Let me go ahead and raise it up a little bit more. See how there's numbers in white, letters in white? Right? That's the only way you'd even know it's in there. So if I put this in there, it just completely disappears. And that's kind of the same thing. So like, nobody's going to admit it because nobody wants to admit that they read here at North Pitt High School. Oh, crap, got that on video. But if Harry Potter, white. All right, so they had that invisibility cloak. Well, they're trying to develop it like an invisibility cloak thing, but when they do, it's going to be revolving around this concept here of refraction. You know what I'm saying? So that's all it is. Refraction is just simply the process of bending light, and when you bend light, like if I can make penny disappear, then I can make if I can make that glass inside the glass right in front of my face look like it's not even there. Well, then I can probably bend light to make it look like I'm not even there. They can use a cloak to cover yourself. The military is trying to try to get that perfected. Now, here's what I do need you to draw. I want you to draw this diagram right here, okay? Because this one here is showing you, again, the rate at which things bend. And you'll probably see that again. You don't need to draw Inspector Clouseau over there on the right side, him and his magnifying glass. But magnifying glass, right? Obviously, what does the magnifying glass do, Donovan?
Enhance, like, vision pretty much, like zoom in on the image.
I mean, you're good. I mean, here's what I'm happy with. I was waiting for him to say it magnifies things. But he didn't do that, right? So what does that mean?
It pretty much, like, zooms in.
What does that mean?
It make things bigger.
Thank you. All right, there you go. Thank you then, Mahomes. All right. See, Donovan can remind me sometimes of those college professors. They know, they're like very, very intelligent. that they don't know how to dumb things down. So I've had a physiology professor that was like that. The whole class would walk out every day. I have no idea what this dude just said. So in the end, we had to read it, we had to research it and learn it ourselves because he taught it, but we don't know what he said. Some people just can't dumb things down. I am great at dumbing things down, which is probably why I'm so successful here at North Pitt. What? No, he didn't. All right. So diagram, bending of the light. Are we good with that one right there? I know some of you still are drawing, but that's refraction. Okay, movie screens. Matter of fact, what we're going to do here a little later is we're going to try to get you to project something on your phone onto a screen, which will just be a piece of paper, just so you can see that refraction isn't perfect. All right, you'll notice that refraction isn't perfect. You'll see there's a flaw when you try to project what's on your phone onto the screen, and then I'm going to see if you can find out how to fix it. Some of you will have a easy way that is not really a fix, and then some of you will have a more challenging task. All right, anybody need more time? Say time. Oh, Donovan's taking notes. He was still thinking about how to say magnify without saying magnify. All right. You good there, Jasmine? All right. Diffraction. Okay. Sounds like refraction. And guess what else has a similarity to it? They also bend waves. Okay, it's also going to bend waves. So in this scenario here of refraction and diffraction, the issue now becomes is, well, okay, if they're bending, then what's the difference between the two? And it's more about what happens after it bends. Okay, and so that's why we have a definition here. It says the bending of a wave as it moves around an obstacle, okay, or it passes through a narrow opening. All right, so if you kind of think about it in this realm, it would be something as similar to this. What do most people, like, imagine when you have a crowd of people and they're all trying to get out one door, okay? What happens to the mass of people as they get to the door?
They get stuck.
They get stuck, okay? Because usually what happens is you have all these people, but then at some point it starts to kind of create that little cone effect, right, where it gets to the door. But then once they get past the door, what do the people do? Do they still stay in a single line?
Oh, they go.
No, they start to then spread out again, right? And that's kind of diffraction there. Is they're trying to get around the barrier, which is the walls, but once they get around those walls, then they get back to spreading out again. They're going to try to fill up the room, let's just say. All right? So that ability to bend around things is why... well, there used to be a young lady at this school called Lexis Acklin. All right, she talked really, really, really loud, and that was her normal voice. Okay, so I would hear her coming to class when she would be over there by Miss Herrera's classroom. Okay, now I would hear her before I would see her because her voice would travel, and when it travels, right, it goes all over the place. Well, I'm not even in the same hallway as Miss Herrera. So her sound waves would get to that little intersection there where the courtyard is, and then it would take a turn and go left down the hallway where my classroom is. That ability to go around, that's diffraction. Okay? It moves to fill up space, all right? Which is different than when a light wave hits a piece of glass. You know, it's trying to get through, but when it gets through, it slows down. So that's why it changes its direction. Well, diffraction is not really a changing of direction. It's a bending around things and going in all directions. So, light in the hallway. Some of you guys, probably when you were kids, probably some of you still now, you just won't admit it, probably leave the light on in the hallway because you were afraid of the dark. Okay? Okay, in the bathroom. Janie admits it. All right? She leaves the light on in the bathroom so that way it leaks. You know, we would say it leaks into the room, right? Well, that's kind of the whole scenario there. Okay? Is that light can bend around barriers too. It can go around things. And so that's why the light in the hallway will go into your bedroom and give you just enough light so that you can see that there are no monsters there. Even though I figured after Monsters Inc. you'd be happy to have monsters in your room. But then again, I guess everybody's different. Charlie, you ever see Monsters Inc? No. Duh. Okay. Wait till you ask me a question. I'm gonna say duh one day. I might hurt your feelings. All right, are we good right there? Now, see right here where it says waves diffract more if the wavelength is larger than the opening or the obstacle. Okay, we're going to kind of show you what that means. Okay, so I'm going to flip the screen unless somebody needs to.
I need some.
You need some more time. All right, Mahomes. I think if she needed it, then somebody else probably needed it too. But diffraction. Let me ask you a question while we're thinking here, while some of you were done writing. Echo, right? Everybody know what an echo is? Yeah. Okay, where's the place where you would normally experience an echo? A cave? Okay.
A gym. Empty room.
A gym, an empty room. Okay. What'd you say, Machala? Wakanda?
A tunnel.
Oh, a tunnel. Sorry. Okay, I got you. All right. So, a tunnel. So, let me ask you this question. An echo. What do you think that would be? Would that be reflection, refraction, diffraction? What do you say, Zachwez? You think it'd be reflection? Okay. And it is. Because what is the sound wave doing? Bouncing off. That's why you kind of keep hearing things over, because your voice travels, hits a wall, hits another wall, and it comes right back to your ears again. So that's why you hear it and you hear it again. That's an echo. That's reflection. I'm sorry, reflection. All right, that's a reflection. Man, I was going somewhere with this. Oh, another place you might hear a good echo. All right, is is a toilet. All right, so Donovan's told me one time that he was trying to be real quiet. He was in the hallway bathroom. He was trying to be real quiet. And so, but accidentally let out a big fart, all right? And then because it was on the toilet, it had that echo, so it made it even louder than it needed to be, all right? And so he said he got a little bit embarrassed with that, right? He's denying it now, so, all right. Maybe you didn't share it. Maybe it was I was walking by and I heard it and I said, the heck was that? Sounded like somebody dropped a bomb in there. Speaking of bombs, somebody in my third period, we call her Deuces because she dropped bombs. Now, don't write. We'll come back. We got videos that make this more understandable. All right, go ahead and write this one down. Now, look on the next two slides, which is when dealing with interference. There's going to be a graph that's got some waves on it. You have to draw the graph and the waves, okay? Because that's the only way you can really understand the idea of interference. Now, interference is simply this. If we have waves going all over the place, it makes sense that at some point those waves are going to collide. Just like if we have cars going all over the place, it makes sense that there was going to be an occasion where a car is going to collide into another car. All right? Well, that's the same idea. Okay? Waves are all everywhere. Waves are everywhere. You got waves filling up this room. That's why you can see. That's why you can hear. All right? But at some point, those waves will start to collide with one another. Okay? And when they do, we call that an interference. And when they interfere or when they collide with one another, they can do one of two things. They can be constructive. What does the word constructive mean? What does construct mean?
To make.
To make. Okay. So usually, what's another word to say to make? If you're in construction, you what? Build. All right. And the reason why I like to say build is because usually you have nothing, and then when you build, now there's something. So that something is something more. All right. Destructive would mean destruct. What does destruct mean?
To destroy.
To destroy. All right. To remove. Right. In a sense. Right. So what happens here again with these two types of interference is when I have two waves collide, what can happen is sometimes those two waves can build a bigger, badder wave. Sometimes when those two waves meet, they can cancel each other out. All right? And that right there, number 2, is what most of you are usually wanting when you buy those super expensive headphones. All right? Except some of you buy super expensive headphones because you want the name brand and it doesn't do really much anything different than the $40 headphones. But go ahead and spend your $300. But noise canceling headphones uses the concept of destructive interference. All right, they are going to have sound waves, one sound wave, another sound wave, they meet up, and when they meet up, they actually reduce the sound instead of build up the sound. That's a noise canceling headphone right there. We'll kind of take a look at that here in a moment. But let's go ahead and get that information written down. Are we good or do I need to go back? You just need number 2. Gotcha. I got videos for this here. All right, but I wanted to get the notes so I can stop the video. And then I'll just say, go to your email and find the videos, presentation thing, and you can go there. All right. Todo está bien? That's German for you good? All right.
I understand. My daddy speaks German.
Okay, there you go. That's funny. I thought I was speaking Spanish, but nonetheless. All right. Constructive interference. Constructive. I just explained what it is. Remember what I said this time? You need to write and draw. So give you some time. Give you some time. We'll have Alondra sing one more time because we have this moment of silence. Oh, we can have Cobra. He's just sitting there chilling. Him and his husky pencil that he has. Doesn't it? Does it say husky on it? No? What does it say? Because it's bigger than your average pencil. For the video purposes, we are talking literally about a pencil. Yes? What does it say? Tackle. Oh, okay. But it is one of those like first grade pencils, right? Yeah. Okay, just making sure. Rosie, you got to be careful when you say a fat one. No, we don't know what you're talking about. You have a good weekend?
Yeah.
Dang, you must have been a good one if you had to really think about it. People watching the video now going, what? Hopefully they're writing this down if you're watching the video. For the past 2 days, I've just played the video to my third period class. Maybe one day I'll record me teaching them, and then play it for you guys. Because they kind of said, like, man, you kind of mean. When I hear me ask my questions to people. I was like, well, let me record teaching you guys and see what first period thinks about how I treat you guys. Maybe you're drawing the diagram. The key here, just so you know, because I don't need all the grids. All right, so let me point to the diagram, then you can draw what you need to draw. That might be easier for you. Okay? Notice right here, okay? So everybody looking up, do me a favor, just to make sure, pencils down, because this is a skill. So I need you to see it, right? Writing it down and trying to figure out later ain't going to help you. All right? Notice you got a red wave, a blue wave, okay? So it's wave 1 plus wave 2. See how it equals? Okay? So these are the two that are going to collide. All right? These are the two that are going to collide. The red and the blue, they're going to collide. That's why they created purple. Now, here's my point. Take a look at the amplitude for wave number 1. What is the amplitude for wave number 1? 2. Okay? What is the amplitude for wave number 2? 1. So when these two collide, they produce a new wave. What's the amplitude of that wave? 3. So obviously these right here, the new wave is bigger than the first. It's bigger than the second. So those two waves collided and created a bigger wave. That's why it's called constructive interference. Got it? So anytime you create a wave bigger than the ones you use to make it, that's called constructive interference. All right? So that's what you want to do. So again, I don't need all the grids. I just need you to make sure that you have a diagram in your notes that has wave 1 looking so big, wave 2 looking so big, and then wave 3 looking bigger than both. That's what I need. 3 waves, but the third one bigger than both. And it's going to be the same thing for constructive, except you're going to have information, you're going to have a wave. But obviously, the wave number 3 in destructive should be what?
Oh, it's going to be lower.
Should be what? Smaller, right. Should be smaller. Like lower amplitude, which would mean smaller. Okay? It shouldn't be bigger. Most definitely should not be bigger. All right, Barney, you still drawing or are you just doodling over there now? You're just doodling. Okay, gotcha. So my third period going to be like, you really got somebody named Barney? Yes, I do. In this world, he's Barney. Barney Bear. If you need 10 more seconds, say 10. Okay. Some of y'all must be like drawing Picassos over there now. I'm about to get Miss Sutton to rate them. Rate these wave diagrams. Alondra, sing the Mexican national anthem. Oh. Watch this, ready? Sing the American national anthem. I was going to say. Garber, sing the Mexican national anthem. No. Sing the American national anthem. No. Jordan, sing the American national anthem.
Can't sing it.
Go ahead, say the first few words. Okay. Oh, what? There you go. He's getting there. He got the first 6 words. All right. It's not like he said okay for a second there, but you know. Oh, say, can you see? All right. Next one. And this is the last one.
You have paper.
Do I have paper? I mean, I got a white piece of paper. Want me to punch some holes in it? Okay. Well then. Oh, she's got a rainbow on her notebook. What causes a rainbow, Janie? Refraction. There you go. Actually, if you're watching this video, go to your email. You'll have an email with a video with a presentation that's got all the videos in that one presentation pertaining to refraction, constructive interference, destructive interference. So go to your email now, watch the rest of it. That's what we're doing now in this class as well. This concludes the recording of this video.